railgun was supposed to be a revolution. It was a gun that didn't need gunpowder, firing a slug at 7 times the speed of sound and reaching ranges of up to 200 miles. Sleek, sexy, and seemingly pulled straight from a science fiction novel, it was a weapon the US Navy just desperately wanted. For years, the railgun was the crown jewel on the Pentagon's wish list, promising pinpoint strikes powered solely by the raw energy of physics and electricity. But by 2021, that dream had effectively died. There were no deployments, no plans for mass production, only a $500 million money pit and a pile of broken test rails. So what happened? How did the Navy manage to fumble what appeared to be a game-changing weapon? And why are China, Japan, and other nations still chasing a dream that Washington's already set aside? Well, this is the story of how the railgun went from a battlefield miracle to a $500 million mirage. A shocking idea. The quest to hurl projectiles using electricity instead of explosives began, surprisingly, actually well over a century ago. Specifically, during World War I, French inventor André-Louis Octet Fauchon-Villeplay built a prototype electric cannon. This was, essentially, the first railgun, and he did it in 1918. The theory was simple. Use electromagnetic forces to accelerate a metal, specifically a magnetic metal, projectile to extreme speeds. In practice, however, it was like trying to bottle light. Early designs remained experimental. Even German scientists experimented with an electric anti-aircraft gun during World War II that never progressed beyond the drawing board. And for decades, that was the extent of the railgun's development. A bit of tinkering here, a bit of fettling there, enough to reconfirm time and time again that electromagnets could indeed make metal slugs go fast, and, well, that was about it. Nothing even remotely approaching a fully realized, ready-to-go weapon system for the real world. And so it was that railguns lived only in research papers and science fiction, a tantalizing what-if that promised to revolutionize firepower if only the engineering could catch up. Little did those early pioneers know that their ideas would spark one of the Pentagon's most expensive wild goose chases a century later. The Pentagon's big bet. Alright, fast forward to the 21st century, and in 2005, the United States Navy, ever in search of the newest war-winning toy, decided enough was enough and placed a daring bet on electromagnetic railguns. They were dreaming big. The Office of Naval Research promised a weapon straight out of sci-fi, a gun that would use no gunpowder, yet could fire projectiles at Mach 7 to hit targets more than 100 nautical miles away, and do it accurately. It wouldn't even need any fancy kind of warhead. Sheer kinetic energy alone would be more than enough here, thanks to the absurd speed. Again, Mach 7 times the speed of sound. To be fair to them, the appeal was really obvious. Name a single conventional cannon that could manage that sort of range, never mind reliably, and you can't because they don't exist. Take the mighty Paris gun. That's Imperial Germany's 282-ton monster designed to lob shells at its titular city from afar. Even it could only manage 81 miles, and that was on a good day. And then there's the M1299 howitzer, BAE Systems' failed attempt at creating an ultra-long-range, yet accurate howitzer for the 21st century, which could reach 68 miles at best. And finally, consider the M65 atomic cannon, for which range was obviously really rather important. It delivered just 20 miles. You get the idea then. An accurate 100-mile-plus range out of a cannon, that's a pretty big deal. And for a time, everything appeared rosy for the Navy's new toy, and by 2008, enthusiasm was sky high. The Navy's Chief of Naval Operations had witnessed a record-setting test of a prototype built by BAE Systems at Darga in Virginia in January of that year, and they liked what they saw so much, in addition to 2 other successful tests in October 2006 and January 2007, that they revised their range estimates even further, now promising 200 miles at Mach 7. Alright, let's consider the railgun's provisional figures in a specifically naval context rather than just as a, other big cannons can't shoot big things so far. The Navy was eyeing it up to supplement and perhaps even replace the 5-inch Mark 45 gun, which has been their go-to ship gun since 1971 and can only push out to 20 miles on a good day. Naturally, with promises like that and progress toward achieving them coming along so nicely, the railgun became something of a military tech celebrity. This claim is best evidenced not only by the vast litany of articles that once discussed it in exciting terms, but also by its appearance in 2009's Transformers 2, in which one is shown giving one of the film's baddies the business from atop a US naval ship. Such enthusiasm demonstrates that at the time, the railgun was widely seen as near-future technology that was just around the corner. By 2010, the Navy had poured tens of millions into prototypes developed by both BAE Systems, as we've already mentioned, and General Atomics. In that same year, the latter began catching up with, and even surpassing the former. General Atomics' Blitzer test system set a new world record by firing a projectile at Mach 5, generating 33 megajoules of muzzle energy in the process. This output delivered roughly the same kinetic punch as a small hatchback car traveling at 100 miles per hour. From there, the Navy began talking openly and even boasting about deploying railguns on warships. The Mach-class destroyers were touted as the first vessels to receive them. At the time, these ships were considered shiny, new, and futuristic, even if in reality they were simply big old piles of still in the process of coming into their own. As for dates, well, officials claimed they wanted to begin testing prototypes at sea by 2016, with a full rollout, as long as testing went well, following as soon as possible. But that rollout date never arrived, did it? How did this happen? How did a technology that appeared to be so full of potential just fail? And that's a good question indeed, one that we're going to answer after we've taken the time to get to grips with how railguns actually work. How to shoot a bullet with lightning. In simple terms, a railgun is essentially a giant electric circuit shaped like a gun barrel. It consists of two parallel conductive rails with a sliding armature or a conductive projectile positioned between them. When an enormous electric current, millions of amps worth, flows from one rail through the armature and into the other, it generates a powerful electromagnetic force known as the Lorentz force. This force launches the projectile down the rails at extreme speeds. In essence, the railgun converts electricity into kinetic energy. Now, to grasp the scale of the speeds involved here, consider that the Navy's goal of Mach 7 translates to about 5,369 miles per hour at sea level. That velocity is nearly 3 times faster than a high-powered rifle bullet and about 5 times greater than the muzzle velocity of the Iowa-class battleship's 16-inch guns from World War II. A projectile moving at such high speeds carries an immense amount of kinetic energy. Even a 10-kilogram slug can hit with the force of a Tomahawk cruise missile. Unlike a missile, however, the slug lacks explosives. It relies solely on its kinetic energy to destroy the target. This means that because the ammunition is essentially just the warhead, without any casing or powder charge behind it, a ship could potentially carry many more rounds. The space usually needed for these additional components is instead used to carry extra rounds. There are further advantages to the electromagnetic technology. For instance, the US Navy has pointed out that removing gunpowder and explosives makes warships far safer from accidental fires or enemy strikes. Meanwhile, you remember the HMS Hood that went up in a fire in World War II? Well, that kind of disaster would be nearly impossible with a powder-free ship. Additionally, eliminating powder results in less noise from the ship's guns, aside from the sonic boom produced when the projectile breaks the sound barrier. In theory, then, a railgun-armed ship could sit offshore and bombard inland targets with precision-guided hypervelocity projectiles, or even intercept incoming aircraft and missiles at a fraction of the cost of traditional interceptors. On paper, these physics look glorious, but theory and reality, they can often be two really different things, as railguns have proven. So let's see what the problem was. Hype meets hard reality. To begin, you remember when we mentioned that railguns to be effective needed millions of amps? Well, it turns out that is actually quite a lot of amps. Consider the light bulb that you're likely sitting under right now. If it's an old-school incandescent type, which it's probably not, odds are that it draws a single amp at most. For those of you watching on your phone, the charger you pulled out this morning probably draws around 1 to 5 amps, and if you're watching this on a really powerful PC, it's likely drawing between 5 and 10 amps as we speak. So, 1,000,000 amps? Well, it's quite a big amount, isn't it? Then there's the matter of actually storing and delivering that massive pulse of electricity to the railgun. Remember we said that the Blitzer set a record breaking 33 megajoules of energy delivered? Well, achieving that required bulky banks of capacitors or advanced alternators, all of which occupied a huge amount of space and weight. Only a few ships in the US fleet, such as the Zumwalt, could even generate enough juice to entertain the idea of running the system. The Navy's most common combatants, the Arleigh Burke-class destroyers, would require a complete redesign to support a railgun, unless the Navy could somehow figure out a several thousand-mile-long extension cord. Those issues might have been solvable, however. After all, this is the US military we're talking about. If anyone could convert a load of ships into floating power banks to support a cutting-edge new system, well, it would be the US military, wouldn't it? When the energy issue is compounded by even more challenges, though, justifying such an effort just becomes all the more difficult. For example, barrel life proved to be quite an issue. You see, firing a projectile, those Mach loads, causes extreme friction along the rails, resulting in intense heat, metal vaporization, and gargantuan pressure. As a result, the rails, typically metals like copper, erode a little, or not so little, each time you pull the trigger. This led to test rails cracking or deforming after just a few dozen shots. The material science simply hadn't caught up to the power of the weapon. Engineers tried stronger alloys and clever designs, but a field-ready railgun barrel that can fire hundreds of rounds without melting down just proved elusive. And what about the rate of fire? Well, the Navy initially wanted a railgun that could fire 6 to 10 rounds per minute to deal with swarming threats. That goal ran into the cold reality of capacitor recharge times and heat dissipation. In practice, testers found it might take at least a minute to recharge for the next shot without frying something. The slow rate of fire also undermined one of the railgun's touted roles, air and missile defense. To shoot down a maneuvering missile, you might need multiple shots in quick succession. After all, these targets are notoriously tricky to hit, and around a minute ain't gonna cut it. Then came concerns regarding guidance and accuracy. A 5-inch dart flying at hypersonic speeds, that's impressive, but only if it hits its target. The Navy did work on a so-called hypervelocity projectile that could be fired from the railgun, and it featured onboard guidance electronics. However, cramming guidance chips and fins into a projectile that must withstand 40 to 60,000 Gs of acceleration and searing plasma presents a material engineer's nightmare. By the late 2010s, when these issues were finally being fully appreciated, the Navy had already spent over $500 million on railgun R&D. Making it ship-ready would require hundreds of millions more for integration and prototypes, with no guarantee that they'd ever actually work. The world tries to catch up. It's also worth noting that while the US Navy very much led the charge, it was far from the only force wrestling with the railgun concept. China, in particular, took note and decided it wanted in on the action too. By 2018, photos emerged of a Chinese warship, the Haiyang Shan, a retrofitted tank landing ship, sporting a massive turret on its bow that looked suspiciously like a railgun. The vessel had been converted into a floating test bed, complete with shipping containers full of what appears to be critical power equipment, and ultimately, it was sent to sea for trials. As early as 2019, US intelligence reports claimed that the Haiyang Shan was effectively getting shots off and at full power, and it might even be capable of hitting targets over 124 miles away at speeds of Mach 7+. A breathless CNBC report in 2018 even went so far as to predict that China's railgun would be operational by 2025. Not so far, beating the US to the punch. And given that, if you're watching this piece early, it's in mid-2025, are CNBC gonna be vindicated? Well, we'd bet a kidney on the fact that while they won't be operational in 2025, they might come at some point in the future. For all its technological flaws and hurdles, China really doesn't seem ready to write railguns off just yet. Back in February 2022, for example, the South China Morning Post quoted researcher Wang Shihou of the China Huiyang Ordnance Test Center, and he revealed plans to, quote, step up testing of railguns to an unprecedented level, with Chinese scientists working to solve wear and erosion issues by refining rail coatings and pulse characteristics. And then came a jaw-dropper. In late 2023, a team at the PLA Naval University of Engineering reported achieving 120 consecutive shots at Mach 6 without serious barrel damage, an endurance milestone that the US never even came close to matching. If true, that's a significant breakthrough. And actually, they didn't attribute the success as being entirely due to ever more exotic and fancy materials used in their railguns' construction, but rather to the software that it's hooked up to. China claims to use a sophisticated AI-powered measurement and diagnostic system that collects data from more than 100,000 sensors simultaneously, over 10 times the number found on a modern aircraft, and then uses that data to figure out exactly how far the railgun can be pushed on the next shot before it gets all blowy-uppy. Of course, Beijing has been characteristically secretive, so confirmed beyond all doubt details are few and far between. However, we do know that their program is led by Rear Admiral Ma Wei-ming, a sort of rock star engineer who drove China's development of electromagnetic catapults for aircraft carriers, so it's not like they're lacking in suitably wrinkly brains. Beyond China, however, India's also been pursuing railgun technology. In 2017, for example, India's Defense Research and Development Organization, or DRDO, successfully test-fired a modest 12mm electromagnetic railgun, accelerating a tiny projectile to about Mach 6. Buoyed by that experiment, India announced plans for a larger 30mm prototype and ultimately a 1 kilogram projectile traveling at around Mach 6. In 2025, DRDO even inaugurated a dedicated center for electromagnetic launch technology to develop futuristic railgun systems. India defense officials tout that such guns could give the Indian Army and Navy a strategic edge, blasting targets in high-altitude border regions or equipping warships with ultra-fast shots against aerial threats. Meanwhile, Japan has also become a leader in electromagnetic guns, a development not entirely surprising given the nation's high-tech pedigree. Their efforts began in 2016 when the Japanese Acquisition Technology and Logistics Agency, snappy name, launched a railgun development program aimed at achieving a muzzle velocity of just over 6,500 feet per second and a barrel life of 120 shots. Impressively, Japan met these goals. By experimenting with different rail materials, switching from copper to other alloys, their engineers achieved 120 continuous firings without significant rail damage. Then, in October of 2023, Japan conducted its first shipboard test of a railgun firing from a test ship. The event marked the world's first at-sea railgun firing since the Chinese tests. And Japan's motivation is particularly pointed as well. They're developing railguns as potential defense against the new threat of hypersonic missiles, a threat further underlined by the fact that their neighbor China, with whom they aren't exactly on friendly terms, has been really stockpiling these missiles of late. The European scene's also noteworthy. The European Defence Agency ran Project Pylon, projectiles for increased long-range effects using electromagnetic railgun, another mouthful, from 2020 to 2023. The project brought together scientists and industry representatives from France, Germany, Belgium, Italy, and Poland to study a naval/land railgun with a 200-kilometer range. By 2023, they reported that results exceed expectations in key areas, from durable barrel coatings that mitigate wear to a conceptual hypervelocity projectile that can survive Mach 6 acceleration. Following Pylon's wrap-up, a follow-on project named THEMA, Technology for Electromagnetic Artillery, now aims to test a full-scale demonstrator by 2028 and possibly develop a roadmap for a deployable system by 2035. In plain English, they're not rushing a railgun to the battlefield next year. Instead, they're quietly working on solving individual pieces of the puzzle and no doubt observing the Americans' expensive lessons with a knowing smile. Global interest in railguns also shows that the concept's not dead. Yet, it has become something of an engineering holy grail, with nations drawn to it despite the US's experience, each believing that they might be the ones who can crack it. As for whether any of these new contenders will succeed where the US has failed, I mean, frankly, who knows? We're not prophets, nor do we have triple PhDs in electrical engineering. But what we do know is that a split in the path is coming. Down one path lies sweet vindication for the US, as all these other countries will end up spending God knows how much money only to discover that old Uncle Sam was right all along and that they should have followed his example. Down the other path, however, we see an Uncle Sam who's a bit foolish because, for once, he actually bothered to cancel a program whose costs were spiraling into the heavens, only for it to turn out that the project could very well have been completed with just a bit more time, a bit more cash, and a bit more belief. And speaking of Uncle Sam, we never actually told you how he came to throw in the towel, did we? So, let's get to that. The end of the line. For the US Navy, the railgun dream officially met its end in July 2021. In a curt, bureaucratically worded announcement tinged with a hint of disappointment, the Navy revealed that it was pausing railgun R&D at the end of 2021 due to fiscal constraints, combat system integration challenges, and the prospective technology maturation of other weapon concepts, end quote. In straightforward terms, the Navy was out of money and patience, and missiles and lasers had simply become too advanced. The final blow came with the quiet termination of the hypervelocity projectile program in the 2022 budget. With that, the American railgun was officially dead. Now, at this point, it's important to focus specifically on the maturation of other weapon concepts remark. We already know enough about the railgun's issues, and there's no need to rehash old challenges. Basically, while engineers were busy tinkering with railguns, guided missiles were improving at a rapid pace, becoming better, smarter, and in some cases cheaper. The Navy had concluded that a $2 million hypersonic missile capable of delivering a precise blow from 1,000 miles away might now be a more attractive investment than a $500 million and counting gun that at best might only reach 100 to 200 miles. And then there's the matter of shipborne lasers. No longer confined to the realm of science fiction, these systems have advanced well beyond experimental lab models and one-off prototypes. Operational systems are now quietly entering service at sea. Leading the charge is the US Navy's Helios system, short for High Energy Laser with Integrated Optical Dazzler and Surveillance, which was installed aboard the USS Preble in 2019. Mounted where a traditional close-in weapon system would typically be located, Helios is a 60 kilowatt solid-state fiber laser integrated directly into the Aegis combat system. Unlike past bolt-on tests, this is a full combat-ready suite that not only burns drones out of the sky but also blinds hostile sensors and provides real-time target tracking. It has already demonstrated its ability to shoot down UAVs in real-world tests, and its only real limitation is the electrical power available from the ship, as theoretically you can fire as long as the lights stay on. And it's not just the Americans taking the lead. In January 2024, the UK announced successful test firings of its Dragonfire system from a static site in Scotland, hitting aerial targets with remarkable precision. Developed through a £115 million joint effort by MBDA Missile Systems, Leonardo, and the UK Ministry of Defence, Dragonfire is expected to be installed aboard Royal Navy warships as soon as 2027. Installation contracts have already been signed for initial 4 vessels. British officials have been blunt in their goals. This isn't about lab curiosity, it's about burning drones and missiles out of the sky for pennies per shot. Meanwhile, across the Pacific, China has quietly joined the naval laser race. In 2024, satellite and social media images revealed a People's Liberation Army Navy Type 071 amphibious transport dock like Simingshan or Yimengshan, equipped with a dome-covered laser turret mounted just behind its 76mm bow gun. The system appears to be designed to counter drones and small vessels and may also serve as a dazzler sensor disruptor. Beijing has reportedly escalated its use of lasers in active scenarios as well. For example, Coast Guard vessels have been accused of shining military-grade lasers at Philippine ships in the South China Sea, temporarily blinding crew members during confrontations at Second Thomas Shoal. In all these cases, the appeal is real clear. Lasers engage at the speed of light and cost almost nothing to fire, merely a few dollars in electricity compared to the hundreds of thousands required for an interceptor missile. They never run out of ammunition as long as the ship has power, and they offer incredible precision, from dazzling enemy optics to searing holes through UAV fuselages. Unlike the railgun, which promised big results but burned through barrels and budgets, naval lasers are here now and are scaling up, quietly transforming the once impossible into just another tool in the arsenal. In short, the railgun lost the race, not against the laws of physics, but also against its own competition. Analyst Matthew Karras summed it up neatly when he suggested that hypersonic missiles and lasers alike had simply leapfrogged the railgun, offering more range, better reliability, and fewer headaches. Why keep pouring cash into a troublesome prototype when other, shinier toys were already delivering? Thank you for watching.